All right, so now we'll take those cost functions that we derived and put in some numbers for our input prices and our short run level of capital. This is going to make these functions a lot easier to work with, so or at least look at. So we've got short run total cost equals, we've got 25 for the wage, and that's 2,500 times 1 plus 100, and that's going to simplify to q squared over 100 plus 100. Now we can plug in these numbers here to our marginal cost equations and our average total cost equation. Or if it's easier, you can take the derivative of this equation with respect to quantity to get marginal cost and see marginal cost is Q over 50, and then divide it by Q to get average total cost. I think that's a bit simpler, but if you plug the numbers into these equations, you'll get the same answers. Okay, so now that we've written out our short-term cost curves for these particular input prices and a fixed level of capital at 1, we'll want to put them on the graph to see what they look like, and then we'll compare them to what happens as capital increases. Okay, so first let's get some numbers here for our graphs. So for total cost, if quantity is 0, total cost is 100. Okay, and then 10, that's going to be 101. Let's see, 100 is going to give me 200. And then 200 is going to give me 500. Okay, so if we plot that on the graph, now you'll see that total cost starts at 100. That's the fixed cost term here. That's my fixed cost. It's equal to R times K. And then at a quantity of 100, I've got total cost of 200, and a quantity of 200, I've got a total cost of, 500. So I can connect the dots there, and I get my total cost when capital is fixed at 1. I'm going to just highlight that. I find that using colors here makes it a lot easier to look at these cost curve graphs. Okay. So we've got a fixed cost of 100, and then you'll notice that the slope of the total cost curve is increasing at an increasing rate. Okay, so unlike the more complicated curves on the previous page, here marginal cost should always be increasing. And you can see that that's true looking at the equation for marginal cost. As quantity increases, my marginal cost is strictly increasing. So if I go to plot marginal cost, you can see at 0, it's 0. See 10, that's 0.2. 100 is 2, and 200 is 4. So 0, 2, and then 4. And this is a straight line here through the origin. That's my marginal cost at a capital of 1. Okay, so my marginal cost is increasing. That's kind of part of how we have simplified the cost curves as they're defined by our Cobb-Douglas function. And the last thing we need to do is to plot average total cost. So this actually is why I've got the 10 in there. You might have been wondering why that 10 is in there, because it's difficult to plot here, but average total cost is actually not defined at a quantity of 0, right? Because I've got this Q in the denominator, so I can't really plug in 0 to my average total cost curve and get something out. And so instead of plugging in 0, I'm going to plug in 10 just to give us a sense of where the average total cost curve starts relative to the y-axis. So, all right, if I plug in 10 to average total cost, I'm going to get 10.1. And then 100 is going to give me 1 plus 1 is 2. And 200 is going to give me 2 plus 1/2, so 2.5. So at 100, my average total cost curve is 2. At 200, it's 2.5. And prior to that, it's like, you know, somewhere up here. So it's going to start up here, come down, and then up like this. So we've got average total cost at capital equals 1. And let's make that green. So now we've got our increasing marginal cost. We've got some fixed cost equal to 100. And the average total cost is important because it tells me the cost of production per unit produced. Now, ideally, we would like to be producing at the lowest cost per unit. If I say society would like to have 100 puppies, most efficient way to get those 100 puppies is to produce at the lowest cost per unit. Now, in this case, we've got fixed capital, so in the short run, you know, you can't always produce the quantity you want at the lowest possible cost, but it is important to recognize where that point is. And that's going to happen at the minimum of the average total cost curve. So right here, where average total cost intersects marginal cost. Now, we have plotted that point sort of by happenstance, or if that's the way I designed the example, so you can see that in this case, that happens at 100, but you're not always going to just get that by happenstance. So we want to be able to solve for the point of production that minimizes the cost per unit of production, or minimizes average total cost. So this is the point where average total cost is minimized. It is important because it is the lowest cost per unit. And so if we want to solve for that point, if we don't have it, we want to solve for it, there are two ways that we can do that. So the first is, of course, to set the equations equal to each other, because we know that that is the point where marginal cost and average total cost will intersect. And the second would be to use the slope of the average total cost curve to define the minimum. So taking the derivative of average total cost with respect to quantity and then setting that equal to 0 tells you where the slope is equal to 0, which would define the minimum point. So I'm going to do this using the first method here, and then in the next example, I'll use the second method. So using the first method, we're going to set our marginal cost equation equal to our average total cost equation. And that's going to give me something that doesn't look too nice, but it's actually not that difficult to simplify. The first thing I want to do is try to combine these terms with the q on the top, and in order to do that, I need to have the same denominator, so I'll multiply the left-hand side by 2 over 2. I get 2q over 100 equals q over 100 plus 100 over q. And then I'm going to move this over here, and it will become negative, so what I end up with is just q over 100 equals 100 over q. And now it might be difficult to see what to do with this, but if you cross multiply, then it gets much easier. So if I cross multiply, I get q squared equals 100 squared. And then take the square root, I will see that q is equal to 100, which of course we knew it was already based on our graphing of this, but But like I said, you won't always get that. So that gives you the point where average total cost is at its minimum.